Yesterday we talked about the general law, Newton's second law for rotational motion. And this is extremely general, okay? Of course, it's going to work for a fixed axis, and we've talked about that before, but it works for an axis translating parallel to itself. It works even when the axis is doing anything. And you don't have to have a rigid body. So as far as I know, this is true. This is true in general. And we've already seen one interesting, and it's interesting and not obvious. We've already seen one consequence of that, and that was the counter-steering example. It's qualitatively consistent with this. So the next thing we want to do, the next natural thing to do here, to study, is suppose the net torque is 0. What happens then? Well, the angular momentum is going to be the total. This is the total angular momentum. It will be constant. So that's called conservation of angular momentum. It's analogous to conservation of linear momentum, where there's no net external force on a system. The linear momentum, or just what we call the momentum, is constant. So this is going to be true. Also, I want to point something out here. Sometimes there's systems where you do have torques, but you may have no torque along, let's say, the z-axis. Let's say you have a fixed axis of rotation. If there is no torque, if the torque has no z component, then the angular momentum about the z-axis will be conserved. Right? So this is a vector relationship here. It holds for each of 3 rectangular coordinates. And if I've got no torque along one of these directions, let's say the z direction, then the z angular momentum will be conserved. So here's a classic example that has a lot of applications, as we'll see. People used to stand on this, but Pasco's now come out with this great, you can stand on it, you guys can see this, but there's a platform here you can stand on it, but this is very low friction, and I don't want to stand on there. Okay? So, maybe they might have done this for old people, I don't know, but they put a stool on there, okay, just a standard stool. So it allows you to sit down, which is much easier, okay? I got this microphone in my... not the microphone, it's the conditioner and transmitter. Okay, so I'm going to start myself spinning, and I have a certain moment of inertia, right? And to enhance the effect, I'm holding these weights. But I could do it like this too, but this just enhances the effect. And I'm going to start off with I've got some initial angular momentum, right? And I'm going to pull the weights in, right? So you can see what happens. I'm definitely speeding up, right? When I bring the weights in. And then when I let them go back out, I'm slowing back down, right? So, what's happening here? We have some initial state we've chosen to be this. You can think of some final state where the weights are closed in here. There's no torque on this system. What you just saw there, you would see out in space. If somebody did this out in space. If some astronaut gave another astronaut some initial angular velocity like this, and then the astronaut pulls his or her arms in, whether or not there's some kind of weight, reduces the moment of inertia, the person's going to speed up. The rotational velocity is going to speed up. So what's happening here is because there's no net torque, angular momentum has to be conserved. And all we care about here is what's going on about the z-axis. So the angular momentum in this case, we've seen, is the moment of inertia times the angular velocity. This is analogous to linear momentum being the mass times the velocity. Here it's the moment of inertia times the angular velocity. So the final value, this is the final angular momentum, has to equal the initial angular momentum. And if I solve for the final angular velocity, I get that the initial angular velocity gets scaled by this ratio. And you can see here that if I reduce my moment of inertia, I'm going to speed up. I'm going to speed up. And similarly, if I increase the moment of inertia, I'm going to slow down. Now, is the mechanical energy conserved here? I have some initial rotational kinetic energy. I have some final kinetic energy. Okay, let's see. I sped up. When I went like this, I sped up. So that's going to increase the kinetic energy. But I reduced the moment of inertia. What does that do to the kinetic energy? So did I just make a mistake there? When I pulled my arms, speeding up is going to increase the kinetic energy, the rotational kinetic energy. However, the moment of inertia has gone down. That decreases the kinetic energy. Do they cancel? No. Which one wins? Yeah, the velocity. And you can you can guess that because it depends on the square of the velocity. You know that you can guess that. But a more physical way of looking at this is, and I invite you to do this after class, you'll feel you are doing work. To pull these weights in, you're exerting a force this way through a distance in the same direction. You are doing positive work. So that means energy has left my body. Where has it gone? Energy has to be conserved. Where has it gone? It's gone into the kinetic energy. It has to be, yes.
So that would play into centripetal motion, how if you have two things spinning and it pushes them out, we're still doing work to counteract that?
Remember, work is force acting through a distance. So if I have two masses here and I'm just holding on to them, preventing them from flying away, right? I'm not doing any work. So I don't know, I'm not sure what you're getting at, but, right? So I have to hold these masses. If I let go of these masses, they're gonna, if I let go of them here, what's right at this point, I'm spinning around and I let go of them, what's gonna happen? This one's gonna fly that way, that one's gonna fly that way. So I have to, because these are in circular motion, I have to exert a force. But I'm not doing any work right now. I'm doing no work right now. The work comes in. Oh, this is much better. This is slower. Okay, I think I can handle this. So now when I do this, I can feel the force that I'm exerting. I'm doing work through a distance. And that's energy that's leaving me, and it's got to go somewhere. It goes into the rotational kinetic energy. And we can explicitly confirm this. Okay? Because we know the final angular velocity. We're going to assume that we have some final moment of inertia that's less than the initial moment of inertia. And we know the initial, some specified value. This tells us how to calculate. Angular momentum conservation tells us how to calculate the final angular velocity. So what we can do here is just calculate, algebraically, in general, the final kinetic energy. There's going to be some initial kinetic energy. The final kinetic energy is 1/2 I final omega final squared. I can substitute in this expression for the final angular velocity. I can square it, look for simplification, and in this case the simplification is to identify 1/2 I naught omega naught squared. That's my initial kinetic energy. So that's how I want to write this. I want to lump the 1/2, 1 power of I naught and the omega naught squared together, and that's my K naught. So look what we have here. The final kinetic energy is a scaled value of the initial kinetic energy, and if I final is less than, what do we get? It increases. It increases. And it really has to, because we're doing, like I said, energy is leaving me. It's got to go somewhere. It goes into increasing the rotational kinetic energy. If we go the other way, now what's going to happen? Well, the math tells us here that if I start spinning, here and go out like this, it tells me that the kinetic energy of the system has gone down. So where has that energy gone? Again, if you do this, you can feel it. When I let if I let the masses go out, I'm exerting a force this way. I got to keep them in circular motion, approximately circular motion here, right? So I'm exerting a force this way. Which way is the displacement? It's that way. What's the sign of the work? The work is negative. I'm doing the system's doing work on me. So that's energy going into me. Now, any questions so far? So this is pretty simple, you know, conservation laws. I think you guys are now finally getting the idea, you know, especially after all that energy work that we did, energy effort that we did. This is really a nice way, you know, when physicists love conservation laws, it's really simple. It's pretty, the idea is pretty simple. This has a lot of applications, as I think probably most of you are aware. Ice skaters, right? And they're masters at this, okay? So they'll start doing a spin with their arms out, but look at their legs. You've got more mass in your legs. When they start a spin and they want to go increase the spin angular velocity, you know, their angular velocity there, they'll start not just with their arms out, but one leg can be out there too, okay? Yeah, so they're trying to start off with the biggest, they're trying to make the initial moment of inertia as big as possible. Then what do? They start to bring their arms in and they just shrink the moment of inertia as much as they can. And it's a very dramatic effect. They spin very fast. I couldn't handle that. They're spinning extremely fast. Right? Anybody do that? Is anybody an ice skater here?
Blades of cooler.
And it's not just ice skaters, right? The list goes on and on. And you can see I put this in here because I think in the past, I may have written this when I taught the course in the sort of later 2000s. Was there an Olympics? You know, there was this Olympics winter sport where these acrobats on ski, they go off a ski jump and they just do all this kind of stuff. That became really popular some years ago. I think that's why I wrote this in here, acrobats, including those on skis. Okay, so they're contorting their body. The angular momentum is going to be, to a good approximation, it's a very good approximation, I would think. It's conserved. So that's the idea. Stars eventually burn out and collapse. And angular momentum has to be conserved. So they're going to spin faster. And in fact, one type of this case is a pulsar. Pulsars are actually neutron stars. They have their diameter is on the order of kilometers. Their density is huge. They're like a giant nucleus of neutrons. So, but angular momentum is going to be conserved, and they rotate very fast. And the reason we know it is they send out electromagnetic waves. They send out a beam. And if the Earth's in the path of the beam, we can get this. It's actually a very accurate timing device. But they're spinning the period here. They rotate several times a second. Our sun takes about a month to rotate once. As you all know, the Earth's polar ice caps are melting, right? How is that going to change the length of a day? So we got this ice up here that's melting. Where's that? It becomes water. Where's that? How's that water? What's that water going to do? It's going to spread out. So the moment of inertia of the Earth will do what?
Expand.
It'll go up because the mass is going to go on the average. It's going to go farther out. So the day will lengthen because of that. Now this is a pretty small effect. I haven't heard of anybody, and I didn't look it up. I'm sure it's been calculated. Okay. What I did look up is this the famous tsunami of 2004. Do you guys remember that? That was caused, of course, by an earthquake. This is incorrect. Okay. The earthquake caused a tidal wave. The tidal effect, the net effect here was to increase the day by 15 the length of a day by 15 microseconds. Okay, but that was due to the tides. The earthquake itself caused a redistribution of mass on the Earth. The effect of that was to actually shorten a day by 2.7 microseconds. That's calculated. So that's what we're interested in here. We're not interested in the tidal effect. So I'm going to edit this. The shift in mass due to the earthquake, that initiated it. the shift in mass caused the length of a day to decrease by 2.7 microseconds. So it was, and you know, it could go either way. It's just there was a redistribution of mass due to this, the earthquake, right? The slippage along the fault here, and it caused a changed the moment of inertia, and it just happened to be, it happened to have made the moment of inertia, because it, I'm getting confused here, it decreased the value of the day, so which way did the mass go? Went out. On the average, mass went, the moment of inertia increased. No, wait a minute. It decreased the period of the day, right? So, I'm sorry. Yeah, I'll fix this, I'm sorry. So, if the mass effect decreased, if the day became shorter, which way did the mass go?
Shrunk.
Yeah, right. It got closer to the axis. Okay. Here's one that you may not know about. It's interesting. The tides are slowing the Earth up in its rotational rate, because there's friction there. Oh, let's see, we got friction. Angular momentum's not conserved, right? It's conserved. We've got this frictional force. The frictional force is going to slow up the angular momentum of the Earth. But what happens to the angular momentum of the water? The frictional force is equal and opposite. So the angular momentum is still conserved. It's still conserved. So, yeah, now I'm going to get myself into trouble. So what I just said was true there if we didn't have the moon, okay? Let me start all over, okay? Sorry. Yeah, this is more complicated than I realized. So here's what's happening here. The Earth is slowing up due to tidal drag, okay? So, and the oceans are carried by the Earth, pretty much by the Earth, okay? So the angular momentum of that, this is, yeah, let me make a note. I now realize that I don't understand this. This is a great time to find that out in front of a class, okay? But I'll get back to you on this, okay? But let me give you this explanation right here. This angular momentum is going down. But thinking of this, neglecting the sun, thinking of this as an isolated system here, the angular momentum has to be constant. So there's only one way out of this. The moon, the angular momentum of the moon has to be increasing. And the natural question is, how can that happen? How does the moon know about this? How can it happen? Well, here, and the explanation is in this diagram here. If the Earth's rotating, let's say this way, we're looking at sort of a top view here. I want to think of it as a top view. It's going to cause a, and there's tides here due to the gravitational effect, okay, of the moon. It's going to shift. Due to the rotation here, it's going to cause this shift. And now if you look at the moon, you see this mass here and this mass here? That's going to exert a torque on the moon. It's going to cause the moon, it's going to exert a torque because of the gravitational effect here. This exerts a torque, this exerts a torque. This is closer than this, so this torque wins out. And it causes the moon to move a little faster, and it increases the moon's angular momentum. So the angular momentum is, in this system right here, neglecting the sun, conservation of angular momentum has to be conserved. And the Earth's losing angular momentum, but the moon is gaining it. And so it's consequently moving farther away from us.
So you're saying that the moon is increasing its angular velocity as it spins around the Earth.
That's right. And it's due to this clump, these two masses right here. These effects don't cancel out because this one's closer. It's not a big effect, but it's the 24/7. It's on all the time. So you can have these little effects that are on all the time, and they just accumulate. So I don't know how much, I can't remember the numbers here, but it's not a big effect. But the first astronauts on the moon put down corner reflectors, right? So we could bounce lasers off the moon, and so we can accurately determine the distance to the moon, and it's getting farther away. Okay, so I'll look into this. Okay, let's do some more demonstrations here. Here's one. I'm going to use this loaded bicycle wheel here. And what I'm going to do is, here's the system. It's got initially 0 angular momentum, right? And now I'm going to give this, the disk some angular momentum. Watch what happens. So I'm going to spin it this way. So which way does its angular momentum point when it's spinning this way? You put your fingers in the direction it's rotating, it's up, okay? So watch what happens here. I'm in an essentially isolated system. Same thing would happen out in space. When I spin it up, oh my. So what happened here? I created this angular momentum going that way, but the net angular momentum has to remain 0 because angular momentum is conserved. Now where's that other, why is it 0? Watch when I spin it up here. So initially I had no angular momentum. There's really low friction here. It's like that's why you can drift. So I spin this thing up. I initially had no angular momentum. I better have no angular momentum. So what is canceling that angular momentum? Well, it's me. I'm rotating in the opposite direction, right? There's something else that's going on here. This has some mass, and it's got a moment of inertia. We could call that orbital angular momentum. So we create this spin angular momentum going here, but the total momentum's got to be 0. So it's compensated for by the fact that I'm rotating around this way. My angular momentum is that way, but I've got this mass that's going around like this, right? That's what we call an orbital angular momentum. What direction does it point? It also points down. So the total, I've created this upward angular momentum, and total has to be 0. So it's being canceled. It's going to add to 0 because of motion of me and the motion of this going this way. Okay, so here, any questions about that? Here's another demonstration. Now I'm going to start it spinning with my feet on the floor. Okay, let's see. Okay, so now we have some initial angular momentum. Well, let's make it up. Okay, so it's going this way. Can everybody see that? So we initially had angular momentum up. Now watch this. I'm going to flip it. Okay, what's happening? So now we're starting off with some angular momentum. It's pointing up, right? And once I take my feet off the floor, angular momentum has to be conserved. If I flip this, now its spin angular momentum is down. We can't change angular momentum. The total angular momentum has to be constant. So what happens is, I'm picking up. I'm going in the opposite direction, right? So we have angular momentum here. Now it's down. But you can see that I'm moving this way. And what's happening here, incidentally, and I should have said, I knew I was forgetting something. Let's go back to the first demonstration. Okay, the first demonstration was this, right? I spin this. How can angular momentum be conserved here? Well, I exert a torque on here. I'm exerting an internal torque, internal to this system, to get this thing to spin. And it consequently develops angular momentum. But what is it doing on me? It's an equal and opposite torque. And it's sending me this way, right? So because these torques cancel in pairs, it's a Newton's third law thing, we're not creating any angular momentum. The torque is always equal and opposite. So whatever angular momentum I create here due to a torque, because there's an equal and opposite torque on me, the equal and opposite angular momentum is going to be created. And the same thing's happening here when I do this. It takes a torque, and I invite you to do this. It's a serious torque. Believe me, it takes effort for me to rotate this, to change this angular momentum. Remember, torque is the rate of change of angular momentum, right? So viewing myself as being outside of this system, it takes a torque to do this. and the torque is changing its angular momentum, but there's an equal and opposite torque on me, so the total angular momentum is constant. So, does this have applications? Yep. Suppose you have a spacecraft or a space station or something like that, and you want to change its orientation. What can you do? You can have a flywheel here that you start rotating, and then you stop it. So I just rotated myself by 90 degrees. Did you see that? Let's do this again. So I'm starting from rest. I wish this platform had a little bit more friction. I start from rest. I go like this. We wait. I just changed my orientation 90 degrees. Okay, here is a diagram. I think this may help with the, I started it spinning and then took my feet off the floor. Okay, so we have some initial angular velocity upwards when it's spinning this way. Angular momentum has to be conserved, so when I rotate this thing like this, I've got to pick up, plus the orbital motion of the wheel, we have to actually develop twice the initial angular momentum in the opposite direction, because the angular momentum has to be conserved. Okay, so any questions? So this is the beginning, there'll be more. These are the simple demonstrations. Okay, and these are the ones that we can quantify at this level. The more complicated demonstrations, we're just going to settle for a qualitative explanation. So let's do let's quantify this. Let's do another quantitative problem here. So let's suppose we have this merry-go-round kind of a disk like this. We're going to assume it's a uniform disk. So we know it's moment of inertia. It's 1/2 the mass times the square of the radius. And we have this person here who walks. Initially the system the disk is rotating at 3 radians per second, and this person's standing at the rim, and the person walks to the center. We want to find the final angular velocity and the change in kinetic energy. And this is a big disk, so we're going to make the assumption that we have what we call a point person. The person has no spatial, is like a particle. We're going to neglect the spatial extent of the person, which is small compared to this distance here. We're going to neglect the laterals. The vertical here doesn't matter. The fact that the person has some height here is not going to matter. We're going to assume this distance right here, the lateral extent of the person, is small compared to that, which is not a bad approximation here. So how do we do this? Well, angular momentum is going to be conserved. Okay, so the initial angular momentum is the angular momentum, the initial moment of inertia is the moment of inertia disk plus the moment of inertia of the person. So for a point person, it's going to be the mass of the person times the square of the radius of the disk, because the person's on the edge of the disk. We can simplify this a little bit, plug the numbers in, and we get a value. So many kilograms meters squared, 1,600 kilogram meters squared. That's the initial moment of inertia of this system. The final moment of inertia of the system, the person is at the axis, and because this lateral spatial extent of the person here is small, we're going to neglect that moment of inertia. It's going to be very small compared to the moment of inertia, so we'll neglect it. So we put 0 here. We just have the moment of inertia of a disk, which is this. So we've got a very substantial change in the moment of inertia here. Angular momentum conservation tells us the final angular momentum has to be the initial angular momentum. The angular momentum here is just the moment of inertia times angular velocity. So like we saw before, we got to get this. We can solve for the final angular velocity. And because we're reducing the moment of inertia, the final angular velocity gets scaled up by this factor. That's what this is telling us. Angular momentum conservation specifically tells us it gets scaled up by this factor of the ratio of the moments of inertia. And we get a number, 7.5 radians per second. It's gone up, more than doubled from the initial value. What about the kinetic energy? The initial kinetic energy, 1/2 I naught omega naught squared, we can calculate that. I get 7.5 2 kilojoules. The final angular velocity, now that we know the final angular velocity, we can get the final kinetic energy. We just substitute it in here. We know the final moment of inertia. And I got 18 kilojoules. So we've had a change in kinetic energy of 10 point difference of this. It's gone up by 10.8 kilojoules. All right? It's more than doubled. And where does that energy come from? Well, believe me, if you were the person doing this, you would have no doubt where that energy comes from. It takes effort to walk to the center of that. You have to exert force through a distance. You're doing work. In fact, if the initial angular velocity was sufficiently fast, nobody would be able to walk to the center. And it doesn't have to be walk. You can imagine, if it makes you feel better, you can imagine you're pulling on some rope or some rod here. You're pulling like that to make it a little bit maybe more dramatic. If this is spinning sufficiently fast, nobody in the world is going to be able to exert enough force to do that. They'd probably have trouble just holding on, okay, not flying off. So there's definitely work involved there. Okay, any questions? Okay, so we're dealing with torque-free motion here, right? This is angular momentum conservation. So it's getting back to this, wherever it is. So we've looked at that, right? Before we move into cases where there's torque, there's a couple of things I want to show you. These are advanced, these are treated quantitatively in higher level courses, intermediate and advanced mechanics, but it's easy to demonstrate them. So I'd like to show you some demonstrations involving torque-free motion here. The first one has to do with an object that has 3 different moments of inertia. Okay, and some objects have 3, they're all different about the axes. An example, the simplest example I think is a block like this where all the links are different. Okay, we did something with this before. What was it?
You've shown us like the cross product.
You flip it, flip it this direction.
Oh, right. Rotations don't commute. If you rotate about one axis and rotate about another axis and you reverse the order, the object ends up in a different, the rotations are not a vector. Right. Okay. That wasn't why this was made. Okay. So here's the idea. These all have different links here. Different links here, here, and here. That means the moment of inertia about these moments of inertia about these axes are all going to be different. And in fact, if you think about this, what's going to be the smallest moment of inertia? Well, it's going to be this one, about what I call the x-axis here, because the mass is the closest there of all the other possible. That has the least moment of inertia. What's going to be the greatest one? Well, see, there's this one, but if you think about it, this is going to have the masses on the average farther out. So the z-axis has the greatest, and this one has the intermediate. And you can look this up, it's in our book. You can look up the values here. You can calculate them knowing these lengths, all right? This has a, this system with all the moments of inertia different has an amazing dynamical property. If you rotate it about one of the axes, like let's say the x-axis, it's boring, okay? It had a little bit of wobble there because I didn't give it just the right initial conditions. That was even worse that time. Let me try the one. Okay, but if I was careful about this, you can see that just nothing interesting is happening here. Similarly, if I rotated about the z-axis, that's easier. See? Nothing interesting. But what happens when I rotate it about this axis? You see that? It's unstable. What it's doing is, it won't stay rotating about the y-axis. It starts to rotate about the other axes. It's an unstable system. Now we can't explain this at this level, but you can see it, it's real. And apparently not everybody knew about this. There's a famous story. In the early days of satellites, satellites typically have 3 different moments of inertia. There's all kinds of things hanging off there. They're not nice symmetrical objects. okay? So, God. So NASA decided in the early days they were going to stabilize. You can stabilize, by rotating something you can stabilize it, okay? Make it less subject to fluctuations. So they picked an axis that happened to be the y-axis. And apparently people didn't know. You know, this is a really simple demonstration, right? Incidentally, it works for a mallet or a hammer. You want to be careful with a hammer. Okay, this has, if you think about this, this has 3 different moments of inertia, okay? This one's stable, but the intermediate one, just like the block of wood, see it tumble like that? And no matter how carefully you do this, it's going to happen. It's going to happen. It's unstable. Evidently, they didn't know about this, so they were trying to stabilize it, and they just picked the wrong axis, and it went unstable. Okay, so any questions about that? As far as I know, this effect has no simple physical explanation, unfortunately. There's another effect, and this is when we have, many objects have an axis of symmetry. Like going down to the center of this cylindrical piece of wood here. There's a dark line we put on here so you could see it when see that it's rotating. If it's not subject to this instability, okay, this only works when you have 3 different values. If I put it up in the air and spin it like that, it's not interesting, right? But that's not the general motion. Oh, sorry. When I throw this up in the air, in this frame of reference, it's like the Earth is not there. So the same thing would happen in space. If I go like this, it would just stay there and it would just spin like this. See, astronauts should do these things. There's probably videos of these things, right? Okay. But that's not the general motion. You see that? It doesn't have to just, that's just a special case. In general, the general motion is, it kind of wobbles like that. And everyone's seen this. When footballs typically are thrown, a lot of times they'll go through this motion like this. We have a name for this, it's called precession. And you can see the precession happening here. That's the general motion. And there's, torque is not involved here. It's just a general motion. Angular momentum's conserved. Kinetic energy is conserved. But that's the general motion. How can angular momentum be conserved here? Got this thing doing this. And it's a very general effect. I can show it to you here. So here, I've set these weights so the center of mass is just slightly below, it's a little bit below the support here. So there's no torque due to gravity. What you're going to see here is the same as if this were out in space. And if I spin it up, one possible motion is that it just sits there. That's like this, flying, you know, doing that, right? But that's not the general motion. That's the general motion. That's what you saw. It looks a lot nicer here, but that's what you saw previously. There's this precession. So how can angular momentum be conserved here? It's easy to see kinetic energy. I have no trouble with kinetic energy here. But how does this conserve angular momentum? Can anybody see that? We've got this spinning, the angular momentum due to the spin, which points this way. It looks like the angular momentum is changing, doesn't it? No, but there's also angular momentum associated with the precession here. We can think of that as an orbital angular momentum. So right at this moment, it's going like, let's say it's going like this, okay? Right at this moment, where's the angular momentum? Forgetting the spin. Well, I've got this mass moving this way, right? So I take R, oh, it's pointing that way. And similarly, this one is pointing in the same direction too. So there's an orbital, due to the precession here. We've got this spin angular momentum. There's also an orbital angular momentum. And one's pointing this way, one's pointing that way. And now you can see how we can add these two things up. There's some axis here. It's precessing about some axis. At this moment, I've got some spin here. I've got some orbital there. You can see how they can add up to give you constant angular momentum. But again, the analysis of that is at a higher level. We can't do that. Okay, any questions about that? Okay, now finally we're going to do add torque. So this is, we all call this a gyroscope. And here's the idea. We're going to look at the system where we have a fixed point here. And here's our object. It has rotational symmetry. This axis right here is an axis of symmetry. This is the typical case. We're going to assume that. And it's spinning. And it's spinning like this. So it has angular momentum this way. It could spin in the opposite direction. In that case, it has angular momentum that way. Now we're in a gravitational field, and this is the fixed point. There's going to be some center of mass of this system. Let's say it's here. All right, taking into account the possible mass down here, and that's especially true with these counterweights here. So right now the center of mass is just below there. But what if I do this? What's going to happen? Okay, the center of mass is here. Okay, so now we have a torque. Now we have a torque, and that's the whole idea here. So the first demonstration I want to show you is with a similar wheel, except this one has a string on it. Okay, so this is roughly what we're talking about here. Except now I'm going to start off with it not spinning. So I'm going to ask you here, what happens if I let go of this end here with my left hand? What's going to happen? It's obvious, right? We know that's going to happen. But we'd better show that it's consistent with this. Would Newton's second law for rotation say it better be able to handle this? It's very general. Can it handle it? Once I release it, where's the torque? Well, we got a center of mass here. I've got this pivot point here. R across the force of gravity acting there. The torque is this way. Where's the change in angular momentum? It starts off with no angular momentum, and then it develops angular momentum. It's developing angular momentum because we have a torque now. So which way is the angular momentum being developed here? Same direction as the torque. We're going to leave it at that. Okay, just be happy. We'll be happy with that. All right. Now, let's spin it the other way. Just to make it. Now, where's the angular momentum? Now it has some initial angular momentum. Okay. If I release this from rest, it can't drop straight down. Ouch. It can't drop straight down. Why? Because if it drops straight down, we still have the torque this way. And the angular momentum now is pointing there. Right? If it drops straight down, where's the change? What's the change in angular momentum? It's here to here. Uh-oh. The angular momentum would be changing this way, but the torque is like 90 degrees from that. So it can't do that. So what it does is, perhaps, I think, surprising. It just steadily precesses. Right? And this happens to be close to 90 degrees. That doesn't matter. The angle's not really important here. So how can we qualitatively be happy with this? How can we reconcile this motion with this? Well, we initially have this angular momentum pointing this way. The torque is pointing this way. The change in the angular momentum has to be in this direction. And is that what happens? Yep. See it? It's changing. The angular momentum is changing in this direction. Now this, what you just saw here was for a fast, if you spin this very slowly, it won't have this nice steady precession. It'll be more complicated. But when it's sufficiently fast spinning, we have this nice simple solution, simple motion, where it does this steady precession around. And that's being driven by the torque. This is not torque free, there's a torque here. So if you have any questions, please ask. If the spin is reversed, the precession reverses. Okay, we don't need to do that. If I spin it the other way, the precession will go the other way. Okay, so now let's look at now this nice gyroscope here that costs a lot of money. Okay, now the center of mass is over here. You can see that if I let it go, it goes like that. So now I've got this situation that we diagrammed there. And now, if I release it from rest, right, that was the first thing we did there. But if it's spinning, and if I give it just the right initial conditions, not bad. That's the steady precession you just saw. There's a torque here. It's pointing this way. It's going around like this. It's causing this angular momentum here to change in the same direction. All right? But that's not the general motion. Let me go in here and hit this thing. Incidentally, what you're seeing is, what's happening here is exactly what you're seeing. There's no batteries, there's no sleight of hand. This is just nature. So what's it doing now? It's still precessing. Is it a steady precession? No. In fact, it's slowing up and then speeding up. It can even retro-precess. Watch this. If I can get it the right initial conditions here. Ooh, that's bad. That's... Now it's precessing. It's actually going back. Okay? And here's something interesting. So before you saw it precessing like this, right? Slowing up and speeding up, but always going in the same direction. Now it's got this retrograde type motion. In between those two cases, it's easy to get the situation in between. You just release it from rest. And now it has a cusp type motion. It comes to rest. It stops. So,
sir, can you show the two right-hand rules again?
Yeah, okay, so let's go back to this nice, that's just a special case. Why didn't we see the more general case here? There's a lot of damping. It damps out very quickly. That's why we didn't see it. Yeah, there's no substitute for good equipment, right? Okay, so there's a torque. The center of mass is over here. There's a torque. Right now, the center of mass is here, right? So from my fixed point here to the center of mass, I have this R vector. All that's important for the torque is you can imagine all the mass to be concentrated at the center of mass, right? So there's a torque that's pointing that way. And this angular momentum, which is pointing this way, it has to change in the same direction. It's got to change in the same direction, and you can see that it does. So it works, you know, it's a sort of qualitative, it works. And it works quantitatively too, okay? So this, incidentally, this dipping motion here that you see, where the precession is no longer steady and it dips, this dipping motion is called nutation. It has a name. Okay? And this can be solved, but it's only done in advanced classes. There's one more thing. Any other questions before we go to the final demo here? When you have, if you want to store energy in a vehicle, in a flywheel, okay, you can store a lot of energy in there, right? The problem is if you're moving along and you want to go, if you want to turn a corner, that's no problem, okay? What if you go, in this case, what if I go up a hill? Whoa! You can feel, I can feel the torque here, okay? So if I'm in a vehicle and I've got a flywheel in there that's stored energy, you could have serious troubles here. So how do you defeat that? I think there's really only one way. Yeah, you need to have the same thing going in the opposite direction. And we have that here. I don't know if you noticed it, but there are actually two, they charge you for the extra, okay? There are actually two disks here that can freely rotate. So I'm going to spin this one this way, this one this way, and now if I let this thing go, what should it do? The angular momentum should cancel, it should fall straight down, and it does. So here, and it takes no, I don't feel any torque here. This is easy to move. But if they're both going the same direction, and you can come by right now, and, you know, you can feel the torque here. It's very noticeable. And you wouldn't want that if you're driving a vehicle that had something like that. Any other quick questions or comments? So you're welcome to come here, just be careful. Don't damage the equipment. And don't hurt yourself. That's the equipment that I care about.